our objective is to use the fundamental theorem of calculus to evaluate definite integrals. Let's start with derivative. What is derivative? What does it mean? Remember that derivative is another way to say the slope of the tangent line. So thinking of a graph, I'll give you a little example to look at. We can sketch something. We'll call this y equals f of x. And I'm going to pick a point somewhere on here, and I'm going to say to find the derivative of this, what I mean I'm finding is the slope of the line that's tangent at this point. So normally, to find slope, I need to have 2 points and do the change in y divided by the change in x. But to find the derivative, that's dy dx. That's the exact slope at that point. Let's take a moment and talk about what is area. Lately, we've been talking about area. Let's just look at a graph. And I'm going to try to draw a similar function to what I drew on the left. And again, I'm going to call this y equals f of x. And I'm going to mark off from one x value, we'll call it a, to another x value b. And when we've been talking about area, we've been saying the area between the function and the x-axis from some x value to another x value. So I'm going to shade in that area so we can get an idea for what we're talking about. And we've said, well, we can't find that exact area. Of course, we've used a limit process, but we started the limit process by saying, let's estimate a rectangle that does a little bit of underestimating and a little bit of overestimating, and we can find the area of this rectangle. Well, how do we find the area of this rectangle? Well, we do the width times the length, or times the height. What's the height of it? That's the change from this y coordinate to this y coordinate, so that's the change in y. And what's the width of it? Well, that's from this x coordinate to this x coordinate, so that's the change in x. So area, this area that we're looking at here, is approximately the change in x times the change in y, its length times its height. So notice these two scenarios side by side. We've done a lot with derivatives, the slope of the tangent line, and it looks like dy over dx, or the change in y over the change in x, versus when we did area, which is the change in y times the change in x. Notice how they are inverse processes of each other. In the slope, we are dividing change in y and change in x, and in area, we are multiplying change in y and change in x. Dividing and multiplying are inverse processes. So what else does this tell us? That tells us that the derivative and well, what's the inverse process of the derivative? That's right, the antiderivative. So whereas slope is the derivative, the inverse process of it is the antiderivative. So now we start to make some connections. If you remember in the previous section, we started talking about definite integrals. Well, a definite integral comes from an integral, and remember the synonym for antiderivative was indefinite integral, so that was that integral symbol, the integral of some function with respect to x perhaps. Well, the definite integral is when we just put those limits in there. So the derivative, or the slope, change in y divided by change in x, is the inverse process of the antiderivative, or the area, change in y times change in x. So now we see that the antiderivative is helping us to find the definite integral. And this is basically the fundamental theorem of calculus.